Head of the department in the Department of Mathematics, Sri Lanka. Okay. He has many qualifications. His academic qualifications are BSc Honours in Mathematics, University of Colombo, Sri Lanka in the year 1999. PG Diploma in Mathematical Modeling in the year 2003. MSc in Mathematical Modeling and Numerical Methods in Italy in the year 2004. PhD in Optimal Control in Colombo in the year 2008. So many more some honors, awards, scientific activities, professional qualifications, etc. are there. Now I leave this stage to Dr. Pereira. Thank you.
Thank you, sir. I feel honored to invite Dr. S.S. Pereira, University of Colombo, Sri Lanka, to deliver the keynote address on the topic insurance aspect of models.
We have to close, no, this one we have to off, no, this one. Yeah. Shall we start? So again, very good morning. So my topic is insurance aspect of epidemiological models, right? Basically, I think idea about like that the beginning I mentioned about that how mathematics change and applied mathematicians came forward and then talk about the applied mathematics, right? So now actually my talk, of course, outline of the talk is this something like this, like I will talk about the applied mathematics, but as basically the mathematical modeling. So the mathematical modeling, and then sort of like infectious disease and their dynamics. Then epidemiological models, trends in epidemiological models in insurance and actuarial science. So if I actually little bit of brief about that, what I want to do is now. I will actually talk about the mathematical model. What is mathematical model and what is mathematical modeling, right? That concept. Then of course we will talk about the basically this biological model, one kind of like a specific kind of model where we want to identify the dynamic of infectious diseases, right? So then we will actually the latter part basically I just want to talk about some of the idea, some of the application of infectious disease models in insurance field, right? It's like something like that. We start with the applied mathematics, but as a one tool, a specific tool which is known as a mathematical model. Then we move into the biological model and the infectious diseases. Then again we come back to the biological model application into the finance, right? So I mean the entire talk, if you can see that how mathematics actually moving into the different areas, and even in that particular area, so there are most of application in the something we call like that unusual areas, you know, because when we talk about the biology, and then if you talk about the finance, so we think like that those two are like disjoint, right? But however, I will try to actually bring to show that now those are anyway intersection, right? So intersected areas, right? So when it comes to the models, right? Mathematical models, right? Mathematical models. What are actually basically, what are the mathematical models? What is mathematical modeling? Oh, let's talk about the basically the models. What do you know about the models? When you talk about the models, so yes, I think all of you are actually aware about that this kind of models, right? So these are models, right? These are models. In fact, now this idea is correct because models mean you want to show something, but you use like a certain kind of like object or item. No, here also what we had done is like basically we want to show that the sort of like some sort of maybe passion or maybe some sort of jewelry or some sort of cloth, right? I think so. We use certain kind of object where to show, show that the now that particular item, right? And then the actually the abstract the people interest, right? So same thing like that. If you look at these things, right? I'm sure that all of you actually done this kind of things in the early childhood, right? So where like you collect the sand and then you try to, of course, construct the sort of items, no? So that is maybe different kind of items, right? So wherever if you go to the beach, I don't know whether we have done, because most of the time in the early childhood we would like to like construct something, and when this water comes and then it destroy like that kind of thing. Those are models, right? Those are sort of like a model, right? Where like all these things we have done in like this models. It's not the new concept, right? Where we have done in even in the childhood also, right? So I mean this figure of course showing you that this actually the constructing this item, which is we use the sort of geometrical shapes which are of course available in the mathematics, no? Triangular shape, then of course the cone, circle, right? Those things. And actually now you can see that the idea about the mathematical modeling or mathematical model mean, which is like that now we have we have problems in real world problems. We call the real world problems, right? So these real world problems, maybe it's an agricultural problem, right? So maybe like that you can see that now you actually paddy field or some sort of like that the yield. So maybe insect problem appear, right? And maybe it is a medicine problem, like a cancer problem, or maybe some sort of disease problem, or virus attack problem, or maybe water, like now this now say example raining, or whether the rain appear or not, and whether the now what will happen next month, whether we get the rain or not, right? Or maybe the how you manage the water, all these things, right? So all these things we consider as a real world problem, right? So there are many more real world problems, but the idea is like that if you look at those problems, we think that those problems can be categorized into the different subject areas, no? Where if it is agriculture problem, you can say it's agricultural problem, right? If you are learning about the maybe chemical reaction, so perhaps you can think about this chemistry problem, right? So likewise, if it is an engineering problem, maybe it is a finance problem, right? But for mathematicians, what you could do is now you can of course try to write down this the problem in a mathematical way, right? So like mathematics is kind of like a language where we have like other language, we have symbols, operators, or grammar rules and all these things, right? So what we do is now in real world problem, we try to convert into the mathematics world. When we actually convert into the mathematics world, right? So we get usually the equations, right? So what are the equations? Maybe differential equations, maybe system of differential equation, maybe partial differential equation, maybe system of partial differential equations, maybe some of the things are system of linear equations, right? Maybe inequalities, right? Various kind of like things can happen. All these, of course, if you get that equation, those equations reflect this real problem, right? Real problem, but that equations or set of equations are known as the models, right? But the models, you can see that now the models reflect the real world situation, real world phenomena, right? And like applied mathematics, we actually talk about the differential equation, partial differential equation. Now you can see that the mathematical modeling is actually the one branch is applied mathematics, but it's not actually the branch, but which is like a global level of the applied mathematics, where we consider the real world problem. So we try to transform this problem into the mathematical nature. So that mathematical nature, we get the model. So I mean the equations. So that equation is equations are known as models, right? Now, so that is model. But what is mathematical modeling? Mathematical modeling is a process. Process means which start from the real problem. So the real problems we have to transform into the mathematics problem, that you get the model, where the equations. Then this equation we want to solve, right? So you have to solve like a differential equation or partial differential equations, right? Those things. So maybe analytical solution is right? If sometimes, of course, the analytical solution is not possible, then you actually talk about the numerics, right? You talk about the numerical thing, or maybe you talk about the different algorithm, right? Various algorithm. Then you talk about the whether the algorithm convergence and all these things, that is known as a mathematical analysis, right? So this mathematical analysis, so you get the results, right? So once you get these results, then that is not the ending process. Then we have to actually validate the model. Validate the model means now the obtained results, we have to look at whether these results reflect the actual problem, the solution of the actual problem, right? So if not, then again you have to find out what is wrong. So what we have to do, I mean, kind of situation. So you can see that the modeling is a process where we start from the real problem and then transform to the mathematics world. Then you get the model, you try to solve it, you talk about the numerics, you talk about the programming language, and then you get the results. The results again you compare with the real problems, you again come back to the real problems, and then again if you actually update the real problem, then again you are moving to here, which is like a circular type process, right? Start from the real problem and there is no ending process, no? Always like you have to update the results, right? So usually now we can say that now what is mathematical modeling, which is like a purposeful representation of the reality, right? So when you take the reality, right? And the other thing is now this in the applied mathematics. So mathematical modeling, of course, exists in this intersection area where you have a mathematics. So where you have a mathematics and then there is a science. Science means any kind of like a situation, any field, right? The problem exists in the any field. So let's say example, if it is a biological problem, the science is a biology, right? If it is agriculture, then the agri-science, right? Anything, right? Then what happened now, you try to develop the model. Once you try to solve the problem, actually you need to think about the computer application, right? So you need to have a program, right? Numerical program, MATLAB, Python, C and various things, right? So we can say that this mathematical modeling is a multidisciplinary area, which is actually the combination of the three situations, right? You can see that the modeling is a multidisciplinary or the interdisciplinary field, right? Which is in the morning also I mentioned that now applied mathematics, so which is of course moving into the moving actually beyond its own boundaries, like because when you talk about the mathematics, this is the mathematics boundary, right? But wherever now we are actually crossing to the mathematics boundary and bring it to the any science, right? And then of course this science, of course, we couple with the computer science, where this intersection area, which is known as a mathematical modeling, right, which is interdisciplinary and the multidisciplinary approach or the multidisciplinary field, right. So again, now we can say that, I think I explained earlier also, something like that. The now mathematical modeling step, you start with the real problem, and then you have you convert into the model, and this model, then you have a mathematical model, then you try to simulate it, write down the programming, right, programming, then which is usually known as a computational model, computational simulation. Then you get the results. Then again, we have to actually interpret with these results with the real problem, right? So then once you obtain this, again you have to actually look at what will happen to the real problem, and again update the model, and again move into the same process, right? Which is like, that's why I mentioned that it is not the circular process, it is always like a circular process, not the circle, circular. Now these are actually our idea is like that, we just want to talk about the infectious diseases, right? You can see that the lot of books, right, all are now well-known books, right, well-known like a Springer books. You can see that now the most of the lot of books, of course, talk about the mathematical modeling in infectious diseases, infectious disease modeling, right, various things, right. So why actually this much of actually the books appear in this particular area? So there is actually something important, no? See, otherwise now, I mean, for example, if these areas is not important, no one of course want to write down this much of books, right? So these are, of course, if you look at if you just go to the website, then you can find the million of books now exist in the talk about this particular infectious diseases, right? Now basically, what is infectious diseases, right? When it comes to the infectious diseases, which is the illness due to the specific infectious agent or infectious disease. Like say example, dengue, right? So then the chikungunya, right? Zika, Ebola, influenza. All these are, of course, spread basically based on the one specific kind of pathogen, right? Or the virus or bacteria. But of course, some diseases are direct, that human to human. Now, for example, influenza, person to person, right? Person to person. But the dengue or the chikungunya, which is not person to person, there is another domain we call vector, right? Via vector. Maybe most probably the vectors are mosquitoes, right? Most of the thing mosquitoes, right? Now this map, of course, showing you like that the most of these infectious diseases, the chikungunya, cholera, dengue, the various things, right? You see that mainly the tropical and the subtropical countries are affected by this particular disease, right? So you can see that now, that is of course mainly the huge area about the world, right? And these of course showing you that the different diseases like Ebola and the Zika, SARS, dengue, and except the SARS, which is of course the SARS is a kind of like a influenza, right? Influenza, you can see that now these three are basically transmit in the tropical and the subtropical region. But in the SARS virus, it of course beyond the tropical region also, right? Now, these are some of the key points, right? The key point. Now, say, when you talk about the dengue, so per year, 390 million dengue infections per year, right? You can, this is a huge number, right? And when it comes to the malaria, you can see that the 2016 to 216 million cases, right? Hepatitis B, hepatitis E, and the various things, you can see that the reported cases are, of course, very huge, million-wise, no? That's why actually as a mathematician, as also the researchers are also, we are also motivated to do the kind of these diseases, no? Like understand why this much of spread is occur, right? Now, this is another point, like where you can see that the most of the countries, like now, especially in the dengue, you can see that the most countries and the most regions are spending too much of money, right? Too much of money to control this one, right? And now, these two, right? These figures, right? And also this economical burden, mainly motivate the researchers right? Researchers to identify the, understand the how infectious disease transmission, right? When you talk about this epidemiological model, right? So it's like mainly the triangular shape situation where you can see that the host is a man, right? Human. Then the agent, there are agents, like sometimes agent are mosquitoes, right? But of course the environment also play the major role, right? Yeah. Now you can see that now if it is a dry season and the rainy season, you can see that the difference between the mosquito density, right? So that means like that we get the idea, environment also play the major role, right? So that's why now it is like when you want to actually understand the dynamic of this disease transmission, we have to actually incorporate with these three scenarios, right? Now this when you talk about the modeling, right? Model, how to model this transmission. So we have a very classical model which is known as a SIR model, right? What is the idea about the SIR model? Which means like that now the population we divide into the several compartments, right? Now the compartment mean you know the train, right? In the train you have a different compartment, right? So the different compartment, so you can talk about the how people move from one compartment to another compartment. So if you consider that concept, then we can actually identify that what is the how the rate of change, right? Rate of people change in the one particular compartment, right? So basically in here the population we divide into the three compartment. One is a healthy people, where we known as they are healthy people. So then these healthy people, when they get the virus, so they are infected. So they are no longer staying in the healthy class, so they are moving into the another class or the another compartment which is known as infectious, right? So the infectious, so then once of the people who are in the infectious classes, so they can get the rest or even they can get the medicine, so they will recover. Once they recover, so they are moving into the recovery class, right? So that is why this SIR model, right? S is a subseptical, I is the infectious, R is the recovered, right? So this is a fundamental concept is now the population is divided into the three compartments, healthy and the people who are having the disease, and also other people is of course the recovery class, right? Now what we do is now we look at how here the population change, right? The population change, what you have to do is now you have to look at that the inflow and the outflow. No? Now for example, if you consider the tank, so in the top of course we get the water into the tank, and the down you are taking the water from the tank. So then if you want to find out the height of the at any point, we want to actually understand the difference between the inflow and the outflow, right? So that is the same thing here also. To understand about that how the population change in the each class, we have to find out the how how the people come to the here, that is inflow, and then they move into the other things which is outflow, right? So basically if you consider the difference between the inflow and the outflow, so we will get the rate of change, right? So that is a differential equation, right? So that is a differential equation. So we can talk about the very simple differential equation, where in a subseptical class, what we do is now in the subseptical class, right? Imagine that the influenza, so in the subseptical class, if one person in here contact with the infected person, so that person might get the disease, right? So that person of course move into this one. So that is the outflow of the subseptical classes. So we can say that now the rate of change of this subseptical class is equal outflow of the minus, which is basically the outflow of this contact, right? So this contact, then there is actually the parameter which is called the beta. Beta is known as transmission rate, right? Transmission rate, right? That one. Then also the infected class, what we can do is now, so infected class, inflow is coming from here. So that's this is this one, and the outflow is, some people, of course, get rest or even they get the medicine, so they are moving into this one, right? So then this way, right? And the recovery class, of course, the inflow is this, right? So basically, what we actually done is now we consider the inflow and outflow, right? And then they develop the differential equation. But here, we assume that in a given a short time period, there are no birth and the natural death, right? Now, for example, otherwise, in this subseptical group, how the people actually getting into this class, which is a natural birth, right? And then also there is another way that some people, of course, leaving from here as a natural death. And here also the natural death, here also the natural death. But we actually forget all these things in the short period, very short period. Like I say, example, when you talk about the influenza, I mean, usually the influenza period is maybe 2 weeks, no? 2 weeks or 3 weeks time, no? When you get the influenza, so it may be like you have to maybe suffer only the 3 to 5 days, no? So basically you can say that the 14 days, right? Now you can see that here there are two parameters. One is a beta, which is usually known as the infection rate or the contact rate. The other one is you can say that the gamma, which is the recovery rate, right? Now this beta actually depend on various other parameters. Now say example, if it is a rainy time, right? So you can see that now the influenza is spread very quickly, right? And of course, if it is a dusty time, again the influenza spread very quickly, right? So therefore, we can see that now these beta and gamma are, of course, depend on the various other factors, right? And wherever now in this kind of situation, you can see that the some of the these simulation things, people start with the subseptical healthy people. So when they actually contact with this one, right? So that is, you can see that now very beginning now healthy people. So when they move with this contact with the infected things, so they are of course getting the red color, which is of course the infected class, right? Now this is of course explaining about the most of the parameters, right? Now what we do is now we actually talk about the which is known as a dimensional form. I don't know whether you are aware about this one. In the most of the modeling concept, what we do is now we would like to work with the scalarless parameters, right? Why then? Otherwise, now what you could do is now you can talk about the if you divide this subseptical class with the entire population, right? Entire population, you can get the now this subseptical class is now in between 0 and 1, right? So it's very easy, we can work with this 0 and 1 value, because rather than talk about the actual values, right? Why? Because if you work with the 0, 1 value, so you can simulate these things, and if it is applicable to the any city, their population is 100,000, you can multiply the final results by 100,000, get the results, right? But if imagine that another village population is maybe 500,000, so you can multiply final results by 500,000 and get the things, right? But wherever if you work with the actual values, what will happen? Then you are working with only that particular area, right? But if you bring it into the scalars form and the work, so that of course you are of course working in the global level, wherever that the results can be applicable to the any other field, right? So any other area. So that's the idea about here. If you divide these things, what happen? Now you can see that here this ST, which is a 0, 1 interval, right? Which is 0, 1 interval. IT is also the 0, 1 interval, right? Also now this we can talk about the ST as, right? Because which is the fraction of subseptical population of humans, right? Why? Because now how we obtained this ST, which is basically the healthy people divided by entire population, which is a fraction, no? If you, now, for example, in one particular village, if you have a 75% of subseptical people, so you will get the 0.75, right? So basically, you can talk about this is also the probabilities, no? ST and IT are also the probabilities. Now, for example, in particular village, if I raise the question, what is the probability that if you select the one person right? One person, that person belongs to the subseptical class, so that person belongs to the infected classes, which is the probability value, but that the probability value is exactly equal to this fraction, right? This fraction, right? Now, wherever we have another point here, which is we denoted by R naught. So, the R naught is actually the beta divided by gamma, which is the ratio between the two parameters, right? This ratio between the two parameters mean, now if you talk about the R naught equal greater than 1, right? So, this R naught greater than 1 mean, what does it mean? Beta greater than gamma. Beta greater than 1, gamma mean beta. What is beta? Beta is the infection rate, right? Which is of course show us like that the how speed disease spread. The gamma is a recovery rate, right? So then idea about like this, if the infection rate is higher than the recovery rate, so imagine that now the 5 people got the disease, but the recovery is only 2. So the idea is like that, you can see that the disease spread so quickly, right? But wherever if you say that the now R naught is less than 1, so the less than 1 means the recovery rate is much higher than the spread, right? So that is, you can see that the now the disease is of course spreading is so slow, right? Actually now this is of course showing you something like that, if R naught equal 2 mean, basically simple way you can say that the one person spread to the 2 person, that 2 person spread to the another 4 likewise. But wherever R naught is half of the 0.5 mean 100 people spread to the 50. Then the 50 spread to the 25. After sometimes you can see that there is no disease. So that is mean we call actually disease dies out, right? Now these are the some of the numbers in the particular diseases, right? You can see that now the disease like this diphtheria, smallpox, polio, and the rubella, various things like wherever you can see that if the this basic reproduction number is so high, it means like that the disease spread so quickly, right? Actually, you can see that now even if you look at the history of the world, some of these diseases, of course, spread in the certain time, so very well, right? For example, now you talk about our smallpox and even the this polio and all these things, right? But of course, like while introducing the certain kind of control strategies, somehow nowadays, of course, people try to, of course, control the most of the diseases, no? Right? Yeah, these are actually some of the how this disease like a pattern, right? So we will now other thing is, now we want to actually talk about the application, right? Now say example, we discuss about that the infected diseases, right? It's a model, right? But that model, now the question is like that, what are the applications? So the application is, one application is basically we can actually identify that how quickly disease spread. It's so that means we can say that that is the itself is application, no? And also now particular thing is, now imagine that now when you talk about this model, you can actually think about like if I actually introduce the control, right? Controls. This example, now we of course start the awareness program, right? Telling the people to actually not to do this and take the certain kind of medicine and all these things, which is known as control strategies. So with this control strategies, that means we actually try to cut down the beta, right? So then you can actually think about okay, now at the moment beta is some higher number, so we want to actually cut down the beta in the halfway. So what kind of things we have to do, right? So those things we can understand, identify via of course via of course discussing about this model, right? That is the application. But in fact we want to actually identify that the some of the applications beyond that is on boundaries, right? So there one is like that, of course we just want to talk about the insurance application, right? So can't we actually think about the insurance or the actuarial science, which are of course known as financial area, right? Financial area. I think if you, perhaps I don't know whether you heard about the actuarial mathematics. So you heard whether you heard about the actuarial science or the actuaries, like a professional is actuaries, right? So when it actually come to the actuaries, Now this is all this insurance, like insurance is a something like that. Now we transform the risk, no? For example, life insurance mean now if we think like that, then now certain kind of like that the threat, what we do is now we transform this risk to the another firm, right? Now for example, in the vehicle insurance, right? So the vehicle insurance mean now if the accident occur, we think like that we don't have much money, or even we think like that this is headache. So we have to find the money to like a recovery. That means the repair the vehicle. What we can do is now we transform that risk to the another person, but you have to pay the premium. So we pay the premium. Now we are not worrying about that, and because when the accident occur, the other party will actually take care of us. So basically the concept of the insurance mean whenever we have a risk, we transform this risk to the another firm, but for that we have to pay. That is known as a premium, right? And also when something happen, so we will get that benefit. We can enjoy the benefit, right? That is actually the insurance. So then when you talk about the actuary, right? Who is an actuary? It's actuarial professional, right? So we will actually talk about, of course, now this is a famous story to demonstrate the difference between, of course, the accountant and actuary, but of course the lawyer. So the idea about like that, the story says that the accountant and a lawyer, also then actuary, so they are walking along the street, right? And when they come upon a man who has just accidentally dropped a number of coins out of his pocket. So then these three people are of course moving into the one road. So three of them of course have seen like that accidentally one person of course dropped a couple of coins from his pocket, right? So what happened now, the accountant so collect these coins, right? And then so then they count the total value and advises the man on how much he lost, right? Now, for example, the accountant of course collect all these things and count the numbers. Maybe it is $100 or whatever it is. Then advise to the man that you have lost this much of money, right? This much of money. And then the lawyer actually ignore the coins and start to searching the sidewalk for the dollar bills, right? That is the usual. Now we look at what is actuary, right? So actuary uses the total value of the lost coins to project what's left in the guy's pocket. So you see that now what happened, accountant always try to maintain the situation. Where the current situation, no? Because accountant of course write down the income and then of course this much of expenditures and all these things, right? Wherever the actuaries also always predict, right? What will happen tomorrow? How much we need the money for tomorrow, or how much we need actually for the next month. Likewise, right? Because you see that now you can see that now is actuaries is something like that the predictor, right, or the forecaster, right? Other than like the accountant is like if everything happened. So once everything happened, of course the accountant can of course say that now okay you have lost this one, right? But before losing the amount, actuaries must say that if you work like this, you will lose this much of money in the tomorrow or day after tomorrow. So which is like that you can see that which is a very highly uncertainty job, right? Because you need like that the mathematics and the statistics in order to predict those things, right? Now when it comes to this ethnology, like the earlier, okay, we actually talk about this ST and IT are fractions. Is a fractions, and then so that now these are the probability of an individual being the susceptible group. I think that we discussed. Now this is actually we can say that this is a probabilistic model, right? And then actually we talk about something like that. We thought like that now as a susceptible people, so they are in a risk. What kind of risk? Because they know that if we get the disease, we have to spend the money, right? Spend the money. So it is a risk, right? So then as an insurance, so what we can do is now we can transform this risk into another firm. Another firm, their idea is like that we can buy insurance, right? But to buy the insurance, we have to pay the premium. why we are paying the premium, the susceptible people are paying the premium when they of course get the disease, so they are moving into the infectious class, so they need the money, right? So they need the money, so those money can be utilized for the hospitalization and all other medical things, right? So that is, we can say that the benefit, right? So the concept is like that the previously, now susceptible people are buying the insurance by paying the premiums, and also the impacted people are of course getting the benefit from this insurance, right? So that's the concept of this one, right? So now you can see that the how each and every person move into the one group to the another one, but via the insurance policies, right? So the basically, I don't know whether you aware about that, the sum of the financial concept, right? Where, because if you are getting the 100,000 in the next year, we want to find out what is the present value of that amount today. Right? It's a very simple idea, which is what you do is now we of course applied the present value concept, right? Now, for example, if you of course getting the 100,000 next year, we just want to find out how worth this 100,000 today, right? So there, of course, what we do is now basically we multiply by this we call actually discounting factor. Discounting factor is nothing, which is 1 over 1 plus I, right? And then of course in the usual domain, sometimes we talk about which is of course the force of interest. Force of interest is ln 1 plus I, right? So basically, now of course you can talk about something, this premium calculation. So we can think about the how much the premium today, right? Today these susceptible people are paying, right? Now the thing is, now we don't know about the exact number of susceptible people. So maybe sometimes the susceptible people are 100, maybe sometimes 200, likewise, no? Which is uncertainty. Uncertainty means now we actually think about the probabilistic way. So when it comes to the probability, you can't find out the exact value. What we do is now you calculate the average value or the mean value, so-called expected value, right? So that's the situation where we talk about the expected value of the premium, expected value of the benefit, right? So this expected value of the premium is if I actually pay in the $1, the present value of the $1 is 1 time this exponential component, which provides the actual present value, and the multiply by the probability. The probability is now this is giving you the uncertainty event, right? So the uncertainty event, then you can find out the actual present value, which is known as the expected present value of the premium payment and the expected present value of the benefit payment, right? Now, from this point of view, we can actually find out what is the premium, where we could of course pay the benefit, get the benefit at the some certain, like after T time, right? After the T time, maybe like after 2 months or after 3 months, right? So there, of course, you will get the 5, but then to compute this one, you need these probabilities, right? So how do you obtain these probabilities? These probabilities from this dynamical system, or where you can talk about you are talk about this dynamical system, right? What we do is now simultaneously we can calculate this premium and with this dynamical system, right? So these are the some of the actually the simulation results you can get. Now you will see that the premium changes with respect to the R naught, right? You can see that the R naught, when the R naught is getting higher, the premium is also getting higher, right? Now these are of course the sensitivities, right? And of course now what we can do is now, this is now example, if you can talk about this one way is actually you can think about this kind of situation where you can of course think about the this simulation model for the different diseases like influenza, SARS, like Ebola and all these things, right? All these things you can actually identify that what is the economical burden in the one particular disease, right? So now say example in the next year, very beginning of the next year, if you calculate these things, right, then you can plan the hospital management and the control plan for the next year. So that that will help you actually to get the, if you are aware about that, now if the economical burden is very high, you can think about the actually allocate the more money to control situation, right? Those are the some of the application in this one, right? Now this is some of the publication and the references. So if I actually summarize what we have done is, basically we start with the applied mathematics, and then the branch we talk about the mathematical model, right? And then the mathematical model of course can be applied the various various field. So we have actually chosen the one particular field which is infectious diseases. Why infectious diseases is so much important? Actually I have shown you like that, taking the different example, now some of the figures, numbers, reported cases, and also the some of the money that the different government and the different NGO, non-government agencies are spending to control this one, right? So there then we talk about a very simple model, how to actually understand how to model the dynamic of this particular diseases, right? Then this application of these models is not only for the disease, even though actually some of the to identify the financial or the economical burden to control these diseases, disease areas, right? So that what we have done, right? So basically like starting from the applied mathematics, then the mathematical model, then the application in the biology, and the biological application again we actually improve into the financial area. So that's the basic idea which we have actually discussed. So thank you, and if you have any questions, or any things, we actually happy to discuss. So
Any questions?
nothing. So maybe thank you very much again.
Thank you. Thank you, sir, for your stimulating session. Session 2 will be started in few minutes.
அது எத்தனை மணிக்கு சொன்னாங்க?
2 to 3.
சார் இங்கே முடிஞ்சு சார் செஷன் சார்.
Once again, I welcome you all for session 2. I welcome the chairperson. I welcome the chairperson, Dr. R. Saurirajan, Head Department of Mathematics, and the keynote speaker, Dr. Udit Pradhat Lianj, on the stage. I request the chairperson, Dr. R. Saurirajan, Head Department of Mathematics, to introduce the keynote speaker.
He is a senior lecturer in the Department of Statistics and Computer Science in University of Kelaniya, Sri Lanka. So he has completed his BSc Honours in Finance, Business and Computational Mathematics in the University of Colombo, and again did his post-graduation University in Industrial Mathematics in Germany. So he completed his doctorate in Industrial Maths in the Germany itself. So he worked as a teaching assistant in the Department of Mathematics in University of Colombo from 2004 and 5, and again he was served as the assistant lecturer in the Department of Mathematics in University of Colombo. So he has been working as a senior lecturer in the Department of Statistics and Computer Science in the University of Kelaniya, Sri Lanka till date. So he worked as a research assistant in the research group Knowledge Management in German Research Center for Artificial Intelligence. Also he was a consultant in Insiders Technology in Germany. So Dr. Lianj is a senior lecturer. Before joining these academics, he worked in the field of IT consultancy in Germany, where he was practicing the CPD framework customized to SRUCM, which is a software project management framework. Now I invite Professor Lianj to deliver his keynote address. Thank you.
Thank you, sir. U is for understanding, issue for others. D is for delight, a surprise from within. I is for intriguing, arousing the curiosity of others. T is for tasteful, the way you communicate. H is for handful, the helpful you are. A is for aptitude, your special capability shine. With immense pleasure, I invite Dr. Udita Prabhat Lianj, University of Kelaniya, Sri Lanka, to deliver the keynote address on the topic Mathematical and Statistical Modeling in Cancer Biology.
Okay. Yeah, thank you. Okay, good. Thanks. Thank you very much, first of all, to Dr. Saurirajan, the head of the Department of Mathematics, and of course, good afternoon to everybody. It is my great pleasure to hear first of all in India, as well as your institute, and I'm honored to see all of you. Well, okay, I guess Professor Pereira, one of my also lecturer, he had delighted with his talk, and also he had talked much about the mathematical models and so on and so forth, so that my work is rather easier. Nevertheless, okay, I'm talking about rather different area, nevertheless still in the area of biology. So we all know that mathematics is language of everything, correct? So we can communicate with many fields in language of mathematics. So beside English today, we speak two languages together. One is mathematics, the other one is the communication language, that's the universal language for us, the English. Yeah. Just to communicate, but we see things in mathematics. Yeah. So it doesn't matter what is the area that we are working with. Mathematics can express all the relations together. That's the idea. Mathematics can quantify things, and mathematics can extract the relationship among different quantities that have been quantified. So that's the basic idea. So being an applied mathematician means what? It is actually being, bearing the responsibility as mathematicians. Because mathematician, if you consider the pure mathematics, something essential for everything, but we focus mainly on mathematics itself. So research on mathematics is about pure mathematics. But applied mathematics, so applying the knowledge that we have acquired in pure mathematics in different field, it's applied mathematics. So actually it's kind of bearing the responsibility. Knowledge mean power. Power mean responsibility. So being a pure mathematician, unless you apply those things in somewhere in other discipline than the mathematics itself, then it's kind of, being selfish. In my opinion, but different people have different opinion. Nevertheless, anyways, the idea is that we try to be responsible and then we share our knowledge and we work together with the other disciplines so that both of our disciplines can advance. That's the basic idea. For example, branch of mathematics called functional analysis. At the moment, depending on the American mathematics classifications, subject classifications, it is belonging to the area of applied mathematics, because the branch of mathematics application itself within the mathematics motivated by the applications which is not belonging to the mathematics actually are in functional analysis. It's a core subjects. Yeah. Okay, that is a general thing about the mathematical modeling I'm talking about. So let's talk about something of application in biology. So this is something quite new trend. Yeah. Even though people try to do the mathematics in biology. For example, history go to the 1905 with the Brownian motion. So Dr. Brownian, he was not a mathematician, he was a biologist and as well as a medical doctor. So, well, he was the person who had first initial idea of the Brownian motion. Everybody knows about the Brownian motion? More or less? It's just random walk. For example, honeybees, everybody knows honeybees. No? Yes, honeybees. So if you think about the path where the honeybees flies, it's just one time here, there, here, kind of, random path. So such motion we called as Brownian motion. Nowadays, it is actually the government motion for many things like financial mathematics. So all the stochastic differential equations, all the stochastic processes, not all, but most of them are governed by such Brownian motion body. Was invented by a biologist, not a mathematician. Yeah. Well, and the today topic, the cancer biology, it's something actually rather new. The history spanned not more than 20 years. So, well, why we are doing biologic or cancer biology, or rather mathematical modeling in cancerology or oncology more specifically? Well, of course, we know that it is 17 million of the people who are affected by more or less in every year in the global level for cancers. Now, Sri Lankan population is 21 million, and if you think about the cancer cases in the global level, it's almost like our own population. So it's quite, pathetic situation why this kind of crisis occur in global level. And of course, among these 9.6 is they end up with expiring themselves. And well, the causes for the cancers are varies. For example, the first day I was in Tamil Nadu, there was a wonderful lecture by Professor Kumaraswaram. During his lecture, he mentioned that in India, somewhere in 1931, the expected life expectancy was something like 31 years old. I'm not quite sure the numbers, but I am referring to his address. Could be true. At that time, people did not live that long. But today it is how many? Anybody knows? 71 years old, yeah, so in general. Due to, facilitating of the medical facilities like the hospital nearby here, and also better foods, availability of the occupation and so on and so forth, that has increased the life expectancy. So thereby actually, well, unknown things, when we live longer, then we might across with the unknown things that we not experienced before. Yeah. So cancer could be caused by something like that as well. On the other hand, actually the pollution that we contribute by ourselves, pollution, and the use of excessive chemicals in our plantation and vegetations, that could cause also high number of cancer cases. On the other hand, habits, our own habits, yeah, like smoking, that also cause for cancer cases. Yeah. First of all, now actually I am focusing on biology, because applied mathematician cannot being in one-sided and do only mathematics. If you wanted to apply something on some other area, we should have to have kind of knowledge in that particular area as well. So that's why many of the people, they find applied mathematics is a bit hard, because it is just out of boundaries. As Professor Pereira said in the morning, if you think about applied mathematics, there shouldn't be any boundaries. If you think about rigid or rigorous pure mathematics, then you confine within mathematical world. So, well, in this scenario, if we apply the mathematical models in cancer, then we need to extend our boundaries, or we need to go through the area of cancerology, oncology. Yeah. So then what is this cancer? Well, of course, we know that our body consists of millions of cells. Yeah. And well, they divide, which means they birth to new cells, and some of them they die out, and some of the cells they just grow and so on and so forth, multiply and grow. So that's the reason why when we get the time, we can grow ourselves. When you're born, you're something like 2.5 kilogram. Now you might be average 50 above. Well, during the time of the childhood, your body is growing, because the birth rate of the cancer cell is much more higher than the death rate of the cancer cell. So then thereby it is growing. And when you become, let's say, over 35 or something like that, then the growing process slowly stops. And then it's become an equilibrium level until 50, 45, 50. Then it becomes the equilibrium level. So number of growing cells or birth cells is more or less equal to number of dying cells. So then our body remains unchanged. Yeah. From time to time, of course, depending on your food consumptions or exercise habit, you may get fat, but that is something else. So it is not a process of body developing. Well, when we are getting older, the other way around of the process, increasing, which means number of dying cells slowly start to increase than number of burning cells. So which means actually the body slowly decaying out, and after some age it cannot sustain anymore, then we die. That's the nature of the world. Yeah. So, well, cancer is what? Cancer is just one stage of a kind of cell stage, which means in a normal setting we have a particular size depending on the organs the cancer cell forms. So cell has a kind of measurement. Cell has some kind of homogeneity depending on the organ where those cells are belonging. For example, cells in lungs, they are differ to cells in your skin. Yeah. So what is the biggest organ in your body? Skin. That is the skin. Yeah. So then, of course, the structure of the cells in your skin is differ to the structure of cells in your heart, for example. Otherwise, you grow heart out of your body. So anyway, the cancer is nothing but abnormal growth of a cell. So we would like to have particular, way of forming the cell, but when it is not in the normal form, then it become cancer cell. Yeah. Well, cancer cell actually it is more robust. Robust in the sense that they actually live longer. Yeah, some of the most of 99% 99 cancer cells, they live longer than other cells. And thereby actually we have a large growth of cancer. I guess I do not present so much pictures because due to the fact that, well, some of you may have sensitivity on different images. So then I just try to avoid many of the pictures because, well, I don't want to make you upset. Yeah. Then this caused by actually DNA damages or mutation and enableness of the DNA. DNA is a kind of constructing structure of any cell. So DNA has the records about all the properties of the cell. So if the DNA is a little bit mutated or corrupted in some way, then consequently the cells, they become different to the other cells which are belonging to the same organ. Something, well, universally know that. That's why we try to find the DNA sequences, infinite long sequences, and based on the DNA sequences, we clarify the characteristic of not only the species but also different cell level. By the way, when I'm talking about different materials, I will point out some of the application at the same time. So DNA application of the DNA in mathematics is quite large because the DNA it involved with the sequences. DNA itself is a sequence of numbers. So working with those sequences, that is actually one part of the mathematics that's called the biomathematics, or if you integrate with the computer science a little bit, bioinformatics, and if you integrate mathematics, statistics and computer science in DNA modifications, then it becomes computational biology. So all those things are actually interconnected. Yeah. So cancerology is also existing in DNA sequences. So that is one area of mathematics where you can apply your knowledge in future. Well, once the DNA damaged or muted, the divided cell get damaged or muted cells, thus cancer will always progress. So some of the facts are still there. Most of cancer cell growth forms tumor, but not all. For example, the excessive growth of this cancer cell, we always sees the visibility of the tumors. If there's a skin cancer, then you have a tumor over there. Inside your whatever organ cancer, you have a tumor. But when it happens with the blood, for example, for the leukemia, you don't have any way to form a tumor because that is a liquid. Well, leukemia is nothing but excessive number of white cells than the red cells, and due to that fact, actually the imbalance or unequilibrium level on the blood, and thereby you get the cancer. Yeah. So, but there is no way to form a tumor over there, but the density changes. Density changes. Yeah. Well, as a consequence of this growth, the structure and behavior of your organ change, and at the end they collapse because they could not work on the way that they're supposed to work. On the other hand, actually, the cancer, some of the people, they think that cancer cells, if it start with one place, then it cannot go another places. But it's not true, actually. It's not true. For example, in the world, most common cancer, any idea? Most frequent cancer in the world, breast cancer. Breast cancer is the most frequent cancer in the world. And it is possible that the breast cancer can develop to lung cancer as well. Because when the cancer is not treated, then it starts to grow, and then it can penetrate the tissues and it can go to other organs, and then the mutation process would transfer to other organ cells and thereby develop cancer as well. So then actually now you get the glimpse of mathematics over there. When something is growing, which mean actually what? Changing the space. Changing the space, we can actually think about process of small mathematical development. So you have a sphere, let's say tumor is a kind of sphere, yeah, which a radius of whatever the r. Yeah. If the radius is growing something like rate per 5 centimeters or 5 millimeters per year, then you can predict. You can predict in how long this tumor would grow to the other places. So those are the simple mathematical models. If you think about a little bit of more mathematical models, for example, when the mutation process is accelerated, depending on different time and so on and so forth, then you can introduce a differential equation. A differential equation to represent the rate change of radius of the tumor. Again, simple mathematical model. Yeah. Well, this is the whole process. It starts with the mutation of the gene and form kind of tumors depending on the cancer mutation, penetrates to the organ. It might go from one organ to another, and then of course whole body collapse. So what are the therapies? Chemotherapy is one of the famous. Chemotherapy is one of the famous. Which means actually we kill the enemy by using another enemy. Because the chemotherapy we use chemicals which are highly toxic. So not only the cancer affect you, but also the cure affect you. So that's the reason why people lose the hair when they undergoing with the chemotherapy. Yeah. There are some other therapies like photodynamic therapy, which is quite advanced and quite expensive. They inject the photosensitive materials to the cancer cells and put a beam of light and destroy them at once. Well, the radiation therapy, that's also there. Radiation therapy is the radioactive, well, basically the ionized radiation. It uses to burn out the cancer cells. It literally burn out. That's the idea. So then, of course, targeted therapy, that is something common, especially in Asian region. Actually, we use the targeted therapy. We use the particular region where the cancer has been grown, and we directly treat that one. Advanced therapy is like gene therapy that repairs the broken or mutated genes. This is extremely expensive and rare. Not all the cancers can be healed by this therapy. So that is actually something advanced. Well, on the other hand, actually thinking about the therapies where we can apply our mathematical knowledge. Lot of applications. So most of the time, the doctors here in not only in subcontinent Indian or South Asian, everywhere in the world, they use their intuitive knowledge to treat the patient. For example, depending on the patient, the stage of the cancer, they decide the amount of injections or let's say chemicals to be used to cure the cancer. Yeah. So they do not actually customize to person. They just have kind of rough idea, mainly the intuition. So that's the reason why we are having good doctors and bad doctors. So some of the doctors, they get a lot of attentions because people, they start to believe, okay, this doctor can heal the person. And it is so. It is so. We see that every day. Because the person, he has much more intuition about, by seeing the patient, he get intuition. Okay, this patient get this much of chemotherapy, then he can or she can cure the cancer. So that is again place. I mean, on one hand, it is we are putting so much into one person's hand about our life. Correct? Because what if that intuition is wrong? What if his judgment is wrong? Yeah. It's a too much responsibility for him or she. We do not know. So if we can take some of the responsibilities out of him, that would be nice. correct? Depending on the body mass context, age, depending on the family history, depending on so many other factors. If we can find out a formula, okay, this patient, given this condition, and the stage of the cancer, and then severity of the cancer, and then the growth of the tumor, all those factors, if we can combine into one and then give kind of rating, give some 5 milliliters about this, of this type of treatment, and that is already good enough. Ne? So then of course those bad doctors has some kind of chance to become a good doctors, and then of course good doctors have better chance to heal the patients. Yeah. So that's a secret about the cancer therapist. Yeah. So they get, if you can develop the intuition, then they can be successful. But we can assist all, regardless, blindly. As mathematicians, as applied mathematicians, we can assist all. So there are many of applications in this area of chemotherapy to cure the cancer. So my aim is not to present so much of mathematical models. My aim is give the awareness so that you can try it out. Because enough resources are there. You can come with your own model. Because if I teach something, which means actually I restrict your mind for that particular area. So I let you be open, and then I'll let you to do your own research in future. Okay, there are various aspects. Mathematical in cancerology, they have a lot of aspects. Basically, as I slowly, gradually explain already. So we can actually think about mathematical simulation and validation and for the control of the biological processes using the mathematical modeling. And of course this one, think beyond existing biological assumptions. For example, the same chemotherapy which I mentioned, we can test in our mathematical model and based on simulation without injecting to a real person. Yeah. So at the moment, most of the clinical testings are done using rats, and then depending on the phases of the drugs, rats and monkeys and everything, and then thereafter humans. So all those steps can be omitted by introducing proper mathematical models. Yeah. Well, analyzing biological system beyond the physical limitation and also some other reasons, you can of course learn them well. Okay, so this is what I mean by simulation. So this is some of the research that we have conducted some long time ago, and this simulation is out from the basis of paper Marias and Dionisio. Well, the idea behind this study was the following. It was about radiotherapy. It was not the chemotherapy. So the cancer in lung, that lung cancers are more kind of aggressive cancers. So lung is a forest. It's like a sponge. It's not like your skin, which is harder, but lung is kind of porous media. So when the cancer is located in somewhere, then if you focus the beam of radioactive materials in order to kill the cancer, it is possible that the beam might diverge due to the forest structure. We wanted to focus in one place, but at the end it is focusing on slightly different place. Then what would happen? Instead of killing the cancer cells, we kill the good cells. So that is the place where mathematician has a lot of work. So via the simulation of the structure, we can mathematically actually construct lungs as a mathematical model sequence of mathematical. Not necessarily constructing all the cells, but basically considering the density, different density of the lung structure. Yeah. So then of course, depending on different density variation, we can guide the laser beam towards the place where the tumor occurs. So that is called the optimization, another branch of applied mathematics, optimization. So actually what we are doing, depending on the patient, depending on the severity, depending on the place where the tumor occurs, we adjust the machine. we instruct the machine so that how to focus exactly on that particular tumor place to kill only, or not, well, I wouldn't say only cancer cells, at least let's say minimum number of good cells, because it is optimization. Yeah. On other hand, I think your head of the department informed me that last or few days ago you had a workshop or conference on statistics. So statistics is also a branch of applied mathematics, if you want to say that. When you encounter with a lot of data, it's mainly you categorize as statistics and develop different tools in statistics. You can do a lot of predictions based on that. Nevertheless, well, different studies like number of cancer people in one particular area, yeah, then there are the different properties like which type of community, male, female, or something like that. You gather the information and then you forecast how many more cancer cases will occur, so that we can have prevention programs if you can find what are the causes and so on and so forth. So that is also part. So part one is a mathematical model. I described them briefly. The power of mathematical modeling truly lies in ability to reveal the previous unknown physical principle that might have been missed by some of more qualitative approach that takes place in biology. So Ostrog is a famous cancer biologist as well as a mathematician, because he has developed a lot of models actually. He's a kind of godfather of cancerology, oncology. Yeah. Especially mathematical modeling. And he said that one actually it's indeed true. Yeah. This is very early models, were not that good actually, started in 60s, but mainly we focus our applied mathematics knowledge in cancerology in last decades or two. So it's a very hot topic if you think about your future career. And well, it was actually not long before we have the Cancer Day, so we're still in the month of February. There are two types of models. And one model is descriptive models. So it is discretized or categorical. Basically, we do not think much about, we do not include much properties about the biological structure of the cancer concerning this type of models. Because we know that cancer is going by cell division process. At one time you have a single cell, and after some while, let's say one day, it becomes two cells. So it's a division process. So when that cell divide into two cells, then it is possible one cell is mutated or no cell is mutated, which means if one cell is mutated, then when that cell become two cells in the next stage, it is possible that both of the cells offsprings are mutated or one is mutated. So it's kind of branching process. So it's kind of division process. It's a kind of random. So we don't need so much of information about the biological structure of the organ or cell to have such simple model. So that's why they actually do not go too much into the characteristic of the tumor progression, but with a little emphasis on biology, we can actually predict the tumor size, tumor shape, as well as population of the tumor cells. So that is one way of modeling. The other way is the mechanistic models. They are actually more into biological details. That's more into biological details. We talk about different resources. So cell actually, let's say, concerning mutated cell or cancer cell, it lives longer. It lives longer. And then actually when, in order to live longer, it needs rather high number of resources. Correct? If you have more resources, the cell can live longer. And for us it is the same. Well, in this scenario or in this context actually, the resource, there are various. One resource is oxygen. One resource is oxygen. So this oxygen resource is high, then actually we can consider, based on the places where the resources are more, we can form mathematical model. Yeah, so a few example of descriptive model. So this is what I mentioned actually, branching process. You started with one good cell and provide one bad cell, good cell, and so on and so forth. This is nothing other than simple probabilistic model. Anybody who does stochastic? Introductory? Do you have a stochastic for postgraduate level? No? So any introductory course for stochastic analysis, you start something called branching method, correct? So branching method, very simple. It's in preliminary. So that branching process actually can use directly to model this cell division process. It's a probability. It's a probability. So what would be the probability of getting the bad number of cells high and remaining the good number of cells same after one cycle, provided that this number of cells are in the system. It's a simple probability. So likewise, actually, you can have the 4 scenarios in order to compute the probabilities, and thereby you can construct this type of tree based on that model. So this actually more descriptive manner. So then actually the probabilistic manner, we compute the chances of having number of cancer cells and dead cells as well as good cells after some time. So that is actually the mathematical modeling in cancerology. And descriptive models, for example, another one is a Moran process. It is there that you have a different number of different type of cells, and then they have a kind of fitness value, which means the robustness value against the cancer mutation or mutation of the DNA. So that is actually, next level of branching process. So in a simple branching process, you have one way of branching. It's one type of cells, but Moran process, which means you have several type of cells, and then they are together branching in different ways, as simple as that. So this is actually the way of calculating the probabilities. So then actually, instead of starting with one cells, you can start with a different number of cells, and then you can predict how many cells population, or what is your cell population after some time. So that's a basic idea. Yeah, so as I mentioned before, they are basically about population and also tumor growth. On the other hand, mechanistic model I briefly introduced, that is actually, it's about the resources availability. So then now most of the time they are spatially also distributed. Resources can be spatially distributed, not only with the time. So then actually it focuses on 2 ways. One is the ODE way, the other one is PDE way, ordinary differential equation, which means it's depending only one variable. So time progression. But if you consider the partial differential equation, it can not only time but also space can be included. That's a main idea. For example, if you think about a population, then that would be ordinary differential equation. But if you think about the density, depending on other factors, then it is about partial differential equations. Yeah, for example, just a population, it's mainly, this is very simple initial value problem, where you can calculate the explicit solution. It's only depending on the time. It's about describing how many number of cancer cells in one particular tumor. So that is simple approach. But well, of course, even though I have showed very simple equation, you can find an advanced one, and also stochastic can be included, and thereby you can have a diverse number of ordinary differential equation as well as stochastic differential equations. PDE models, they are different. For example, as I already mentioned, cell growth depending on the resource. So it is, for example, you know, when you always see the trees in everywhere, ne? Especially the coconut trees over here. So they just usually grow straight away. But if the coconut tree encountered with some obstacle or some other tree, it just turn, yeah, to seize the lights. Okay? Turn and then it grows. Correct? So cancer is always like that. Cancer search the resources. Cancer cells. So if one place has lack of resources, other place has more resources, then it goes towards the place where more resources are there. So that is actually the idea of mechanistic models. So you have a partial differential equation model. It describes the density of the oxygen concentration as well as, of course, the density of the tumor or cancer cells and give kind of relation. And then the idea is that depending on the distribution of oxygen, how to predict the structure of the cancer. So that is the basic idea. All right. So that's simple models that I would like to introduce so that you can work with more advanced models and also explore the world of cancerology, oncology in the point of view of mathematical modeling. But I would like to give kind of small type of statistical models so that you get much more intuition. Because remember that, especially in the fields like biomathematics or biology, applied mathematics applied on biology, you cannot survive only by considering applied mathematical techniques. You have to go for statistical techniques as well to build the preliminary construction or initiate the research. So this is I'm talking about other scenarios which I had briefly mentioned. Community problems, like within the population, per particular time period, we see that many cases are occurring. So study of such cases based on data, it's mere, of course, depending on the statistics factors. For example, analyzing the factors that affect on such progression of the cancer in particular area. Yeah. So one type of research that we often conduct. Yeah. Example study I present, that's something we have done some quite time, one or 1.5 years ago, which is actually identifying the risk factors causing the cancer. That's what we have done. Well, we consider the breast cancer because breast cancer is the most common cancer, not only in the world, but also in Sri Lanka. Yeah. So what we did actually, we collect so those are our objectives, identifying significant risk factors causing the breast cancers in Western province in Sri Lanka. And then mainly we try to focus on cancer patients who were visited in different clinics and then gather the data based on, of course, questionnaire. Yeah. And using that data, we try to do statistical analysis to identify what are the factors. Can we do that alone? Let's say we are either mathematicians or statisticians. Can we do that alone? Do we have any clue about factors? No. We have to combine with domain specialists. So we conducted this study with our medical faculty because in our medical faculty we have a different department for cancer and surgery. And over there are specialists who are in breast cancers. So their knowledge is very important. Actually, they provide, okay, I'm thinking that the smoking is influencing cancer. But he thinks that, he or she doesn't know that. So then we work together to clarify whether really smoking is affecting on cancer. So that is by a statistical analysis. So this is actually combined work. And of course, well, that's we involve with people. People have different opinion. People have different mindset. Correct? Diverse beliefs and so on and so forth. So we have to be very careful. We need to follow ethics because we cannot just go and ask things from a patient. Imagine a patient in a cancer institute. He or she suffers a lot. Over a lot of that suffering, if we ask to fill a huge number of questions, then that will be a catastrophe. And also, we cannot just go and interview a cancer patient because we need to understand his or her situation before. Then we need to be educated, especially in psychology, to address. So you see now, we initiated as a mathematicians. Now we are going to do something on cancerology, but at the end, we go for psychology. So everything is connected. So that's what exactly Professor Pereira said. For applied mathematicians, there is no boundaries. Yeah. But it's at the same time, it's quite interesting because you encountered with a lot of different disciplines as well as the people from different disciplines. Yeah. So, well, we had collected this number of cancer patients and this number of 145 the controls, and of course they were in between 35 to 70. And people who did not like to be interviewed, we exclude and so on and so forth. And the idea was that based on the literature as well as based on the opinion from the domain expertise, which mean the doctors who studied a lot about clinically about the cancer, we collected a lot of type of variables, let's say factors that could lead to cancer. For example, age, BMI category, biomass index, you know that whether you are thin, underweighted, normal weighted or overweighted. That is, and then race, religion, occupation, pork or beef consumption, which mean the food habits, yeah. Material status, education level, alcohol consumption, and so on and so forth. And of course, family history of cancer, and so on and so forth. Many other things. So we found that age categories that really depending on the cancer, and then of course the gender, it's normal. By the way, not only women can have the breast cancer, but also male can have the breast cancer. Yeah, it's something like 3% of among the males they get the breast cancer. Most of male do not treat for the breast cancer because they wouldn't think that is a breast cancer. So consequently, what would happen? Actually, the cancer spread into the lung when it has been identified as a cancer. So that is most unfortunate situation for the males compared to the women's. Yeah. So there are many factors. All these factors were newly identified. Among them, the productive period of the breast cancer, how span. For example, your youngest child is 14 years when your last child is born, which means the productive period is quite long. So those things also affect. And also the age of first birth of the children. And also BMI category, first degree ovarian relatives, whether your mother had a breast cancer or not, or grandmother had a breast cancer or not. That's highly depending. If your family has a breast cancer, then please undergo for test. It's available. It's available everywhere in the world now. It's nothing to be ashamed. It's just a test. When you are over 30, then you can go. But before that, there is a less probability you get a breast cancer. Yeah. And also if you had your mother and grandmother both had the cancer, then well, unfortunately, which mean actually you get more chances to have the breast cancer. Okay. Some other factors like the side of the breastfeeding. Most of women, they are right-handed, then they feed the children from the left side of the breast. So then they get the cancer on right-hand side. So there are many other factors. These things were found in our small research. And also we developed very simple model to find out the risk index. So that's how we assisted the doctor. So as soon as you go to the cancer, at the moment, based on our research, some of the institutions, some of the clinics, they provide a questionnaire. When you go to the cancer, I mean, not to treatment, but to test. Yeah. Then you get a kind of questionnaire, and that questionnaire includes the questions based on our findings. And depending on the answer, we give a kind of rating or index. So based on the index, for example, if the index is more than 6, then you have a high chance to get the cancer. So before on hand, the history of the patient is also evaluated and also given some kind of glimpse for the doctor. So whether the patient or whether the person could have cancer or not. So those type of research are there in cancerology. I do not want to go into too much of details in the mathematics because I was advised that the audience over here is, you are new to mathematical modeling and you are still studying applied mathematics in the beginning. So I did not want to confuse you by putting a lot of mathematics. Rather, I wanted to, give some kind of new area of a field where we can apply our knowledge. And this area is getting much more famous, and also it has a kind of sentimental value for us to work with, because at least if you visit a cancer hospital and then if you see the situation of the patients, that is actually rather pathetic. So then as a mathematicians, not confining our work to blackboard or piece of papers, we can assist them to be cured. And also by doing that, we actually, we ourselves create a better future for us as well. Okay, findings of, these are what findings of our research. I don't want to go too much into details. Nevertheless, that's the idea is that both statistical and mathematical models can assist for cancer, not only cancer prevention, but also curing the cancer, because mathematical model exists in every places. Okay, so that's all I wanted to share. I hope I did not exceed the time. Well, any questions? No questions? Okay. So that, thank you. So that actually, when I don't get any question in my lectures, there could be two scenarios. One, I am utter failure. I just wasted the time. Or I am so nice, I could have explained everything so that you can understand. But I would go for the middle, because I know that within 40 minutes or 45 minutes I cannot explain everything. Nevertheless, my idea was to give kind of intuition and kind of introduction to the area of this. Okay, thank you again for your attention.
Thank you, sir, for your stimulating session.
So thank you very much, sir, for your session is very much informative, and I think all the participants must have got some knowledge about how the mathematics is applied. So as of now, you have thought nearly it's more or less very informative, and it's more or less a lecture session, I think so. You have gone into so deep that everyone will understand what is behind those cancer cells and etc., and how it is applied, how mathematics is applied in that. Thank you very much, sir. Thank you, sir.
An announcement for participants. I request other college participants and B.Ed college participants to go for lunch and be back sharply at respective venue for paper presentation at 2 p.m. And our college paper presenters are requested to stay back here now. Our college paper presenters are requested to stay back here now. Students are requested to give attendance to their respective tutors after the lunch.
Except Except the paper presenter, other students are requested to go for lunch and be back here sharply at 2 o'clock.